Alrighty, this is our second day on antiderivatives, or also known as indefinite integrals. And as with everything that we've seen so far through our calculus stuff here, the second part of a lesson, if it ever says continued, normally involves having to do what we've learned, but instead we use trig. So, ergo, trig into antiderivatives as we continue our learning on this topic. Some basic integration rules that we have here that are going to help us along the way, which are just going to make it easier for us to do this work. We've got these basic rules here. If we have the integral of cosine x dx, that is the same thing as sine x plus c. Sine x is the same thing as negative cosine x plus c. Secant squared x is the same thing as tangent x plus c. Again, these are going backwards. So instead of taking the derivative of something, now we're going backwards. So just kind of remember, what is the derivative of tan x? Well, it's secant squared x. So it's the derivative of sine x, it's cosine. It's the derivative of cosine, it's sine, but because this is negative, it makes it a positive sign. And again, you can see the rest of these, 4, 5, and 6, different basic identities or rules for integration. Alright, so now, as an example, on this first one here, we've got secant y times tan y minus secant y dy. So we're doing this with respect to y. And that would be the same thing as, again, as long as we have the little integral sign here, we're not taking the antiderivative yet. We're just simplifying this to make it look like something we can work with. And so in this case here, we're going to actually distribute the secant y into tan y minus secant y. So if we do that, we're going to have secant y tan y minus secant squared y, and then obviously all that times our dy, or with respect to dy. Alright, so if we look back at our rules or identities, this is secant x plus c for this first term. And again, we talked about this in previous lessons here. By distributing this, we get into a scenario where we're going to have an addition or subtraction, which simply means we can take the derivative of the first part, subtract the derivative of the second, or antiderivative of the second part. So we have antiderivative of this minus antiderivative of that, and it keeps us from having to do any kind of product or quotient type rules in this scenario. So by distributing, we get this into two separate integrals, and then now we can take this part right here, which we said is going to be secant y. And I'm going to save the plus c. The plus c we know will end up being at the end. But, and we talked about this obviously in our previous lesson as well. We could end up with 2 or 3 plus c's in here, but still c plus however many c's you want is still just c. It's just some constant. And so we'll just combine our c's into one here. This next part, minus and secant squared x, is the same thing as tan x. So this is going to be tan y. And then, like I mentioned here, we'll have plus c. So this should be the antiderivative, or the integral, of secant y times, parentheses here, tan y minus secant y with respect to y. And that's pretty straightforward and pretty simple, hopefully. And again, we're doing this video because we've got some students out, so hopefully this will help them while they're out, so that we can march on in calculus and attain all the goals we have set before us. Yes, we try not to forget about those who are not here. We try to include them in everything that we do. So, to those who are listening and watching, this is a great shout out to you guys. We care about you. Okay. Example 2. Find the equation of y for the given derivative and through the indicated point 3, 8 on the curve. So we're finding dy dx with, equal to x squared, And so we're going to take the, let's look at this here, f of x is going to be the derivative, which I didn't do a great job of that one, the derivative, the antiderivative of x squared with respect to x. Okay, so we know this by rule. We can go ahead and just take the antiderivative or the integral at this point. This is going to be, this is derivative of y, or f of x, with respect to x. The respect is, question was asked, are we doing it with respect to y? But we're taking the derivative of y with respect to x. The one on the bottom determines which one we're taking with respect, we'll say. And y is the same thing as f of x, so f of x or y, you could put it y if you wanted to, is going to be this x squared dx. Alright, so now, we know that this is going to be x cubed all over the exponent of 3, so all over 3. That way, if we were to take the derivative of this, 3x over 3, x squared, the 3's would cancel, you get x squared. So seeing that that goes forth and backwards is correct. And then we're going to go plus c. And so now it's asking us to find the equation for y of the given derivative through this indicated point 3, c. So let's plug in some values so that we can find out what c should be. We've talked about the c, and we just kind of let it sit out there on its own. But now let's go find what c is. We know that at a certain point, we can plug in for y. Let's go ahead and just do that here. This is actually y, same thing, right? This is the same thing. So y equals this, and we have a y value and an x value. So why can't we plug in those values and determine what c is? And thus giving us the answer that we're looking for here in finding this equation. So y is 8, x is 3 plus c. And if we multiply 3 times 3 times 3, we get 27. Divided by 3 is going to be 9. And so 8 equals 9 plus c. And if I take the 9 over to the other side to isolate c, to find out what it is, c is going to equal a -1. And that's all we need. That's all the parts we need here to finish out writing the equation. So the equation is going to be y equals x cubed over 3 minus 1. And that's it. Not too much involved in that one. Again, we're just finding c from the given values that they presented here for 3 and 8. The point at 3, 8. All right, now example 3. Find f if f double prime is 12x squared plus 6x minus 4. F of 0 is 4. F of 1 is 1. Okay, those are going to come in to play here in a minute. But so the first thing we know, if we go backwards one step, so we're going to take let's do this, f prime, or first derivative. We've got the second derivative here. We're going to go backwards to the first derivative. It's the same thing as the integral of 12x squared plus 6x minus 4 dx, okay, with respect to x. So if we're going to go, let me move this up here so we can have more room to work. If we're going to go and take the antiderivative here, the integral of this, we're going to end up with 12x cubed over 3 plus 6x squared over 2. And when we learned these rules previous lesson here, you're going n plus 1 over n plus 1. So n is your exponent here. We're going n plus 1 over n plus 1. Minus 4x, and that's the same thing as 4x to the first over 1, but we don't have to write that because it's understood. And then we have to add in our constant. Right, that's the first derivative. We can simplify that, and I'll just do that kind of on the next step. Now we're going to go back again. Oh, sorry. We're not going to do f prime. We're just going to go to f of x. Okay, so now we're going to f of x. And that's going to be the integral of this that we just found, which was f prime. So reducing that, that's the same thing as 4x cubed plus 3x squared. And then here, this is still minus 4x and plus c dx. Okay. Now, this step is going to present us with a little bit of something new to look at. I'm not going to say it's difficult or hard. It's just something new. Okay, so now when we take the integral here, you're going to have 4x to the 4th over 4 plus 3x cubed over 3 minus 4x squared over 2. And notice what's going to happen here. C is some constant. We don't know what that constant is, but what did we do with the constant 4 a while ago? Well, we just multiply it times x. So now C is going to have to be multiplied times x, and it's x to the 1 over 1, or n plus 1 over n plus x to the n plus 1 over n plus 1. And now we'll have to add another letter to represent our constants in this step, or the original function here, f of x. So we'll put a d there. If this were to go one more time, let's say we started with the third derivative, you may end up having to go to letter e, or so on and so forth. Okay, so now let's look at something here. Okay, we have a question. We're going to pause here because Jocko has a question. Go ahead. Oh, wait, so the question is just to ask about the cx again. Okay, now, remember we've got a constant. And for us to have a constant, let's say that c equal 2. If that had been a 2, what would have this been? As the integral of 2, it would have been 2x. So we don't know what this constant is, but we know whatever it is, it's multiplied times x. And so that's why we end up with this term, cx. Okay? And as we move along, maybe it'll make a little more sense. If we need to explain further, we will. Let's look at a few things here. And as we go through this integral, you know that you're going to take and raise your exponents and put it over the top, or put everything over that. And then as you get here down to these last terms, we know that 4x, you got to raise it to x squared, but this had to have been an x term. If it wasn't an x term, it would have become a 0. So since this was an x term, it has to have an x involved in it. Again, if this was a 2 or if this was a 3 or 4 or whatever, we know it was just a 3x, because we taking the derivative would have just taken that constant and left it there in the derivative itself. So now that must have been some constant times x, and the x went away when we took the derivative. Okay, moving on to the next step. We know that f of 0 is 4. So if we multiplied, think about this, we know that f of 0 is 4. Therefore, if we look at this last equation that we got, which is f of x, if x was 0, that would mean that all of these terms would have gone away, right? All of those terms would have gone away. X equals 0 leaves us with d being the only thing left in that equation. So if f of 0 is 4, then, cute little dots, therefore, d must equal 4. Yes? Does everybody follow that logic? Okay, so now we know what d is. And it also gave us that f of 1 was equal to 1. So now, can we plug 1 in, and the 4 that we just found, and solve for the cx, or solve for c, inevitably. So this means that we can say that if the whole thing is supposed to be 1, is going to equal, plugging in our x terms, the 4's will become a 1, so this is just going to be 1 to the 4th plus 1 cubed, make that a little bit better, minus 2 times 1 squared, because this 4 over 2 becomes a 2. So it's 2 2 times 1 squared, all right, plus c times 1 plus 4. Now, the only variable left is the c, and in that case, we can obviously solve for c. So now, we end up with c, if we take all of these, multiply them out, we're going to have 1 plus 1 minus 2, so that's a 0. So then we end up with 4, and we still have 1 on this side. We take the 4 across the other side here. That makes it a negative 4. Negative 4 plus 1 is a negative 3. So doing your math there, and we just kind of walked our way through it, talked our way through it. These two here all cancel out. We end up with 4. Move it to the other side, makes it negative. So we have negative 4 plus 1, and it gives us a negative 3. So now, our f of x is x to the 4th plus x cubed minus 2x squared minus 3x plus 4. So given a few pieces to the puzzle, some few pieces of information, we can find the original function. Even though we know we're going to have constants involved, we can find the original functions, the actual function itself, the equation for that function. As long as we're given a few pieces here, we can find that by some process of elimination and a little bit of logic. All right? Let's look at the last example, example 4. A particle moves in a straight line and has acceleration given by a of t, acceleration, with respect to t time, is equal to 6 plus 4. Its initial velocity v of 0 is negative 6 centimeters per second, and its initial displacement s is 9 centimeters. Find its position function s of t. S of t. So we're trying to find s of t, the original one. We have basically we have the second derivative of s, do we not? Remember that if we took s of t and we took the first derivative of that, okay, so s of t, first derivative was equal to velocity, right? And then we said, okay, well, double prime of t is equal to the prime of velocity, or that's the same thing as a of t. So we want to find s of t. We've got a of t. In other words, we've got s double prime t. So let's go backwards and find that out. So again, rewriting this here, this is what we have. It's the same thing as velocity, derivative of velocity, which is the double prime of t. So we're going to have to go back twice to find out what the displacement or position function is. Position function is for s of t. Okay, so now the s of t, the velocity, which is going backwards from acceleration, is going to be the derivative. The integral, antiderivative, the integral of 6t plus 4 with respect to t. Okay, so this is, make sure I make those t's so we can see those correctly. All right, so 6t plus 4 with respect to t. And if we take the integral of that, we know that that's going to be 6t squared all over 2 plus 4t plus c. Going ahead and looking for c itself, we know that velocity, when velocity is 0, the whole thing should equal negative 6. So if I set this velocity at 0, it's supposed to be negative 6, well, then I should know that that's going to make all of these 0. C is going to equal negative 6. I plug in 0 for t here, 0 for t there. All I'm left with is c, so c has to equal the negative 6. Alright, so there we go. That helps me out because now v of t is equal to 3t squared, taking the 6 over 2, simplifying that down to 3. 3t squared plus 4t minus 6. Okay, so now I've got this to work with to go back one more to find the position function s of t. So now, let's move up here. The position function is going to be equal to the integral of the velocity function. Right? The velocity function we said right here was going to be 3t squared plus 4t minus 6. And then again, this is going to be with respect to dt. Or with respect to t. Okay, so now s of t is going to equal t cubed, or 3t cubed, all over 3 plus 4t squared all over 2 minus 6t plus, we don't want to use c because we already used it down here, let's use d again, plus d. Well, it also gave us that when the original function, when this function right here, the original function is 0, the displacement is 9 centimeters. And so because when s of 0 is equal to 9, we can deduce, right? We can deduct, therefore, that d equals 9. And that gives us all the pieces we need. So we can plug this in. We'll simplify these as we write it. S of t is going to be the function t cubed plus 2t squared minus 6t plus 9. That is our answer. Now, before we stop the video, do you guys have any questions that may be the same questions that Shelby or anybody else watching may have? Yes, we have one question. Mr. Jocko, once again. Okay, so the question was asked at this point, how do we know that c was negative 6? If we take this velocity function, that is the function for the velocity, and we take that, we know velocity at 0 is supposed to equal negative 6. So velocity at 0 equals a negative 6. That means that when I plug a 0 in, this function, let's see here, this velocity function right here, right? This is the velocity function. It's going to be 3t squared plus 4t plus c. If all of that equals negative 6 when t equals 0, then that means negative 6 is going to be 3 times 0 squared plus 4 times 0 plus c. Okay, move this up where you can see it. So that goes away, that goes away, c is going to equal the negative 6. So when they give you this velocity equal to 0, anytime you have a 0 given up here, you know that that's just going to be the constant variable that's left. The constant is just going to equal whatever is there. So hopefully that answers your question there. We can find that out here. And then again here, the same thing happens. We plug in a 0 into the position function. It gets rid of all the t terms, and d has to equal the 9. So that gives us all the pieces for this final equation for the function, position function. Okay, hope this has helped you, and we'll hopefully see you in class very soon. You guys have a great day.